Earlier, we have seen that electrical effects are caused by the movement of free electrons, and electric current flow is the most obvious of these electrical effects. For example, in a cell, when the terminals are connected to an outside circuit, free electrons flow from the negative terminal to the positive terminal, and we say that an electron current flows. So electric current is the flow of electrons in a conductor from negative to positive. But you'll remember we sometimes refer to conventional current, which is thought of as flowing the other way. Suppose we have an electron current flowing up a vertical wire and passing through a piece of card. It might seem an odd thing to do, but if we try the iron filings trick, we may be surprised to find that there is a magnetic field around the wire. The lines of force are circles with the wire at the center. And they flow either clockwise or counterclockwise, depending on the direction of flow of current in the wire. Here's how we find out which. You imagine yourself gripping the wire in your left hand. Note that left hand with your thumb pointing in the direction in which the electron current is flowing. Then your fingers will point in the direction of the lines of force. In the case we saw, we said the electron current was flowing up the wire, so using this left-hand rule with the thumb pointing up in the direction of electron current flow, the fingers indicate a clockwise direction for the lines of force. If the current flows down the wire, then the left-hand rule tells us that the lines of force have counterclockwise direction. If you want to draw this field, you need to show in your drawing if the current is flowing into the paper or out of it, toward you. Well, think of a dart. If it's flying directly away from you, you would see the flights looking like a cross. So we show current going into the paper with a cross. On the other hand, if the dart was coming straight at you, you would see its point. So we use a dot to show electron current coming toward us out of the paper. These symbols are called dart notation. Using dart notation and the left-hand rule, we can draw the field around this wire showing the direction of both field and current. Current coming toward and field clockwise. Now let's look at a wire bent around and round to form a coil. When current flows through it, there will obviously be a magnetic field of some sort around the coil. And if we perform the experiment with the iron filings in this case, we discover that the magnetic field produced by a coil is very similar to that produced by a bar magnet. Again, we need to know the direction of the field, and this is found with another left-hand rule. You wrap the fingers of your left hand around the coil, pointing in the direction in which the electron current is flowing. Then your thumb points to the North Pole end of the coil. Three things affect the strength of a magnetic field produced by a coil. First, the more turns there are in the coil, the stronger the field produced. Second, the greater the current flowing, the stronger the field produced. And finally, adding an iron core to the coil concentrates the lines of force into a stronger field. And we now have the device known as an electromagnet. Some of the strongest magnetic fields of all are produced by big electromagnets. Now let's think about a most important idea to do with electric current. When we connect the terminals of a cell to an external circuit, electrons flow as a current. But there has to be a force driving the electron current around the circuit, and it is called the electromotive force, or for short, EMF. It is measured in units called volts. Whenever you find two bodies at a different state of charge, if you connect them, there will be an EMF driving a current between them. Now, it isn't necessary for an object to be negative and the other positive. If we have one body negative and the other still more negative, that is, it has accumulated more free electrons, and we then connect them, there will be an EMF between them to drive electrons from the more negative body to the less negative one. Before the two bodies are connected, we say that there is a potential electron flow between them. We say there is potential difference between them. Potential difference, or PD, is also measured in volts. It becomes the EMF as soon as the bodies are connected by a conductor. If there is no potential difference, there is no EMF and no current flow. But speaking of conductors, you'll remember that good conductors are substances with easily detached electrons, which allow current to pass easily. We say they have low resistance. Good conductors are silver, aluminum, and copper, and also carbon and water. And they, remember, have low resistance to the passage of current. Poor conductors, on the other hand, have high resistance. Substances like these with very high resistance are called insulators. But resistance depends on three other things apart from the nature of the material. First, the length. The longer the conductor, the higher its resistance. A greater EMF would be needed to drive the current through it. Next comes the cross-sectional area. The larger the cross-section, the lower the resistance. It's as if there was more room for the electrons to get through. And finally, there's the temperature. The hotter the material of the conductor, the higher the resistance it will offer to the electron flow. So, resistance also depends on temperature. Now, usually, the conductor carrying an electric current is a wire, and it is surrounded by a covering of insulation so that the current can't leak away. The resistance of the insulation itself, obviously, has to be very high indeed. But the longer the wire, the more chance there is of the current leaking away through the insulation. So the lower is the insulation resistance. On the other hand, if you double the thickness of the insulation, the harder it will be for the current to leak away. So the higher the insulation resistance. In this part of the course, we have talked about the magnetic fields produced by current flow, and we have seen how they form the basis for the electromagnet. We saw the left-hand rule for the direction of lines of force round a wire, and we heard about the dart symbols for current direction. Then we talked about electromotive force and about potential difference. And finally, we had a look at the resistance of conductors and at insulation resistance and what they depended on. In the next part, we will discuss the most important law in electricity, Ohm's law.